So given a Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13 and so on, how would you compute the nth term here? How does the nth term look like? How can we even answer this question? Let's say, what is A50 here? So one way to do it is simply start from 0, 1, 1, 2, 3, 5, 8, 13 and so on, and then go up to A50. The other way to do it is write A50 as A49 plus A50 is A49 plus A48. And then A49 is A48 plus A47, A48 is A47 plus A46, and keep enumerating this, and as you proceed you will only get A1s and A0s completely, and you know what that is, and then you will find what is A50. Is there a closed formula which tells us what is AN in general? Yes, there is. Let's see how to do that. Let's recall our just now refreshed knowledge on recurrence relations. So let me write down the recurrence relation for Fibonacci sequence. AN is AN minus 1 plus AN minus 2. You see, we know how to solve this. We write down what is called the corresponding quadratic equation, r square minus r minus 1 equals 0. And then we find out that this is a quadratic equation where the coefficients a is 1, b is minus 1, c is minus 1, and I plug in the formula minus b plus or minus square root of b square minus 4ac divided by 2a, and substitute for ABC, and I will get AN is equal to, the root R is equal to 1 plus square root of 5 whole by 2, and the second root is, as I said, plus or minus square root of b square minus 4ac, which is 5 basically, b square minus 4ac. So the second root is 1 minus square root of 5 whole by 2. These are the two roots of this quadratic equation, and we know how to write what is called the general solution. So AN will be equal to alpha times the first root plus beta times the second root, and this root should be m power to n. So AN will be alpha times 1 plus root 5 by 2 whole to the n plus beta times 1 minus root 5 by 2 whole to the n. What is this alpha and beta? Now look at this. What is A0? In Fibonacci sequence, A0 is 0. But A0 in this equation happens to be alpha 1 plus alpha 2. Correct? When you put n equals 0, these terms become 1 and you are left with alpha plus beta. So A0 equals alpha plus beta, which is equal to 0. Correct? And then A1 will be equal to, put n equals 1, you get A1 equals alpha times 1 plus root 5 by 2 plus beta times 1 minus root 5 by 2, and this is going to be A1, which is 1. Now these are simultaneous equations, as you can see. So solving it, a little bit of jugglery, as you can see, gets me to alpha being equal to 1 over root 5. Simultaneous equations, it has a unique solution. And beta is minus 1 by root 5. Now I have a complete solution for my AN. Just plug these alpha and beta there, and you will get AN is equal to 1 over root 5 times 1 plus root 5 by 2 whole to the n minus 1 over root 5 into 1 minus root 5 by 2 whole to the n. Now A50 is easy to compute. Simply put n equals 50, you will get the answer for A50, which is the 50th element of a Fibonacci sequence. Pause and think how. A simple looking Fibonacci sequence, which is given by AN equals AN minus 1 plus AN minus 2, can involve this much of math.